Look up at the night sky, where countless stars trace the glowing river of the Milky Way. But there's more here than meets the eye. Hidden in the darkness between those shimmering lights lies an invisible force, shaping everything you see. Our galaxy isn't just made of stars and gas, it's cradled in a vast, mysterious halo of something we can't see, touch, or even fully explain: dark matter. This ghostly presence holds the Milky Way together, its gravity weaving an unseen web that stretches far beyond the glittering spiral arms we admire. Why does this cosmic cloak defy everything we thought we knew about the universe? Tonight, let's drift into the mystery together, floating through the questions that keep astronomers awake under these same stars. Close your eyes and picture it, the galaxy's hidden embrace, the quiet pull of the unknown. Where does this journey find you? Are you nestled under city lights, or wrapped in the hush of open countryside? Whatever time it is there, let the wonder of the night carry you deeper into the story of the galactic halo, where science and mystery dance in the dark. Now let's travel back in time to the moment when this cosmic mystery first began to unfold. The story of dark matter doesn't start with high-tech telescopes or supercomputers. It begins with a brilliant but often overlooked astronomer named Fritz Zwicky. In the 1930s, while studying the Coma cluster, a group of galaxies millions of light years away, Zwicky noticed something bizarre. The galaxies were moving far too fast. According to the laws of gravity, the visible mass of stars and gas in the cluster shouldn't have been enough to hold them together. They should have flown apart, like marbles scattering from a broken string. Yet there they were, bound tightly in space. Zwicky called this the missing mass problem, and though his peers dismissed the idea at the time, he was the first to point at the shadows and say, "Something is there." Zwicky's work was ahead of its time, but the puzzle only deepened decades later, when another astronomer, Vera Rubin, turned her attention to individual galaxies. She found that stars at the edges of spiral galaxies, like our Milky Way, were orbiting just as fast as those near the center, defying Newton's laws. Imagine a merry-go-round where the outer horses whip around as quickly as the inner ones, despite being farther from the center. Without an invisible force anchoring them, those stars would have been flung into the void. Rubin's observations became undeniable proof that galaxies were enveloped in something unseen, something massive. The scientific community could no longer ignore the whispers of dark matter. But what exactly was this hidden substance? Theorists began to piece together clues, ruling out ordinary matter like planets or failed stars. If dark matter were made of anything we knew, it would interact with light, revealing itself in telescopes. Instead, it seemed to communicate only through gravity, tugging at the universe from the shadows. The modern concept of dark matter took shape, a mysterious particle, unlike anything in the standard model of physics, woven into the fabric of space itself. Some proposed WIMP, weakly interacting massive particles, while others imagined actions, ghostly specks born in the early universe. Though we've yet to catch one directly, their gravitational fingerprints are everywhere, from the bending of light around galaxy clusters to the delicate ripples in the cosmic microwave background. Zwicky And Rubin's legacies remind us that science often advances by chasing the invisible. What began as a nagging inconsistency in galaxy motions has blossomed into one of cosmology's greatest quests. And as we'll see next, this ghostly halo around the Milky Way isn't just a curiosity, it's the scaffolding upon which our galaxy was built. Now let's turn our attention to the woman who transformed dark matter from a fringe idea into an undeniable truth. Vera Rubin was an astronomer with a quiet determination, armed with meticulous observations that would shake the foundations of astrophysics. In the 1970s, while studying the rotation of spiral galaxies, she uncovered something that defied all expectations. Stars orbiting far from the galactic center were moving just as fast as those near the core. Picture a river where the water at the edges flows as swiftly as the current in the middle. It shouldn't happen unless some unseen force was at work. Rubin's discovery hinged on galaxy rotation curves, graphs that plot the speed of stars against their distance from the center. According to Newton's laws, stars on the outer edges should have been slowing down, like planets farther from the sun. But Rubin's data showed flat curves. No matter how far out she looked, stars raced along at the same breakneck speed. The only explanation, an enormous halo of invisible matter, its gravity gripping the stars tight, preventing them from flying off into space. Her findings were revolutionary, yet the road to acceptance was anything but smooth. Many in the scientific community dismissed her work, clinging to the belief that galaxies were made only of what we could see. Some even suggested that Newton's laws might need revising, a radical idea that seemed more palatable than accepting an entire unseen universe. Rubin faced skepticism not just because of her conclusions, but because she was a woman in a field dominated by men. Her persistence, however, was unshakable. She kept gathering data, galaxy after galaxy, each rotation curve telling the same story. Over time, the evidence became impossible to ignore. Other astronomers began confirming her results, and the term dark matter shifted from speculation to cornerstone of cosmology. Rubin's work didn't just prove the existence of dark matter, it revealed how much we'd been missing. Up to 90% of a galaxy's mass, she showed, was invisible. Imagine realizing the house you've lived in for years has hidden rooms, their walls shaping everything around you. Yet Rubin never claimed to have solved the mystery. She often said, "We don't know what dark matter is, but we know it's there." Her humility and curiosity epitomized the spirit of science. While others sought grand theories, she focused on the data, letting the universe speak for itself. Her legacy lives on in every modern telescope, trained on the galactic halo, in every experiment hunting for dark matter particles. Vera Rubin didn't just change how we see galaxies, she reminded us that the cosmos is far stranger and far more wonderful than we ever imagined. And as we'll see next, the tools we've developed to map this invisible realm are just as extraordinary as the discoveries they've brought us. Now imagine standing at the edge of a vast, pitch-black lake, unable to see what lies beneath the surface, yet you know something is there. Every ripple, every disturbance in the water hints at the unseen depths below. This is how scientists study dark matter, by observing the subtle ways It bends the fabric of space itself. One of the most powerful tools in this cosmic detective work is gravitational lensing. Picture the universe as a trampoline, with galaxies and clusters acting like heavy weights that warp the fabric. When light from a distant object travels past these cosmic heavyweights, its path bends, much like a car's headlights would appear distorted if viewed through a glass of water. Dark matter, though invisible, adds to this warping effect. By measuring how the light from background galaxies is stretched and twisted, astronomers can map the distribution of dark matter, tracing its ghostly outline across the sky. The Hubble Space Telescope has captured breathtaking examples of this phenomenon, where entire galaxy clusters act as cosmic magnifying glasses, revealing the hidden scaffolding of dark matter behind them. But lensing isn't the only clue. Take a closer look at the way stars and gas clouds move within galaxies. Just as Vera Rubin's work showed, stars on the outer edges of galaxies orbit far too quickly to be explained by visible matter alone. Think of a merry-go-round spinning so fast that the children clinging to the outer bars should be flung off, yet somehow they stay in place. The only explanation: an unseen force holding them tight. By studying the speeds of these stars and the behavior of hydrogen gas clouds, scientists can calculate the gravitational pull of dark matter, effectively weighing the invisible halo that cradles each galaxy. Then there's the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light reveal how matter, both visible and dark, was distributed in the early universe. These patterns are like fingerprints, showing where dark matter's gravity clumped together, pulling ordinary matter into the galaxies and clusters we see today. Satellite missions like Planck have mapped these fluctuations with stunning precision, confirming that dark matter isn't just a galactic curiosity, it's woven into the very foundation of the cosmos. Even more intriguing are the collisions of galaxy clusters, where dark matter separates from ordinary matter like smoke parting around a speeding train. In events like the Bullet Cluster, hot gas visible in X-rays slams together and slows down, while the dark matter, unaffected by anything but gravity, sails straight through. This leaves a telltale signature. The visible matter and the gravity waves appear in different places, as if the universe itself is pointing to the invisible culprit. Yet for all these methods, dark matter remains elusive. We see its shadow in the motions of stars, its fingerprints in the bending of light, its echo in the heat of the early universe, but the substance itself slips through our grasp. It's like hearing whispers in a dark room, each one a clue to the shape of something we can't quite touch. And as we'll soon discover, the hunt for dark matter's true nature takes us to some of the most extreme environments on Earth and beyond. Now let's turn our gaze closer to home, to the Milky Way, our own cosmic neighborhood. From Earth, we see its glittering spiral arms arching across the night sky, a river of stars so dense it appears as a faint milky band. But what we see is only a fraction of the story. Beyond the familiar disk of stars, gas, and dust lies something far more expansive, a vast, invisible ocean of dark matter, stretching hundreds of thousands of light years into the void. Picture the Milky Way as an island in this ocean, The glowing disk of stars we admire is like the shoreline, visible and vibrant, while the dark matter halo is the deep, unseen water surrounding it, so immense that it engulfs everything we can observe. If you could shrink our galaxy down to the size of a dinner plate, the visible disk would be no larger than a coin at its center. The rest, dark matter, silently shaping the galaxy's fate. This hidden structure isn't just a passive backdrop. It's the scaffolding that holds the Milky Way together. Without the gravitational grip of the dark matter halo, the stars in our galaxy's outer reaches would fly off into space, like sparks from a spinning firework. The halo's pull keeps them in orbit, even as they move at speeds that defy the laws of visible gravity. And just as ocean currents guide ships, the dark matter halo steers the motion of smaller galaxies orbiting the Milky Way, like the large and small Magellanic clouds, which dance under its invisible influence. But the halo isn't uniform. Imagine stirring honey into tea. It doesn't blend smoothly, but forms swirls and clumps. Similarly, supercomputer simulations reveal that dark matter isn't evenly distributed. It forms intricate streams and filaments, remnants of smaller galaxies torn apart and absorbed by the Milky Way over billions of years. Some of these streams, like the one left by the Sagittarius dwarf galaxy, weave through our galactic neighborhood like cosmic brushstrokes, visible only through the subtle tug they exert on nearby stars. What's even more astonishing is how far the halo reaches. While the Milky Way's visible disk spans roughly 100,000 light-years, its dark matter extends at least 10 times farther, a staggering volume of space dominated by the unseen. This means our solar system isn't just orbiting within the galaxy. It's submerged in this invisible sea, with dark matter particles flowing through us every second, unnoticed. Yet for all its scale, the halo remains eerily quiet. Unlike the disk, where stars are born and die in spectacular supernova, the halo is a realm of silence. No light, no heat, just the faintest gravitational whisper. It's a reminder that the most powerful forces in the universe often leave no trace for our eyes to see. And just as sailors once mapped the oceans by the stars, astronomers today chart this dark ocean by its effects. By tracking the motions of distant stars and the distortions of background galaxies, they've begun to sketch the outlines of the halo's hidden geography. Each new observation is like dropping a sonar pulse into the depths, revealing a little more of the Milky Way's true form, a form shaped, above all, by the invisible hand of dark matter. As we'll soon discover, this hidden structure isn't just a feature of our galaxy. It's part of something far grander, a cosmic web that connects all the galaxies in the universe, a web whose threads are woven from the same mysterious substance. But here's the fascinating part. How do we even begin to understand something we can't see? To unravel the secrets of the galactic halo, scientists turn to the digital realm, where supercomputers act as time machines, reconstructing the Milky Way's birth and evolution over billions of years. Imagine feeding the laws of physics into a virtual universe, then hitting play. These simulations start with a young cosmos, filled with a smooth soup of dark matter and gas. As gravity goes to work, dark matter begins to clump together, forming invisible scaffolding. Gas follows, pooling in the densest regions, igniting into stars and galaxies. Over eons, the Milky Way emerges, not as we see it today, but as a dynamic, ever-changing structure shaped by dark matter's relentless pull. What's striking is how these simulations reveal the halo's messy, unpredictable nature. You might expect dark matter to spread evenly, like ink in water. Instead, it clumps and twists into intricate webs, with dense knots and wispy filaments. This isn't just artistic interpretation, it's a direct consequence of dark matter's gravitational dance. Smaller clumps, called subhalos, orbit within the main halo like bees around a hive, each a remnant of ancient galactic building blocks. Some of these subhalos are so dense, they should host their own dwarf galaxies, yet many remain eerily dark, invisible even to our telescopes. These simulations also solve a cosmic puzzle: why the Milky Way's outer stars orbit so quickly. Without dark matter's extra gravity, our galaxy's visible mass couldn't hold onto these speeding stars. The simulations show how the halo's invisible embrace keeps them in check, its gravitational fingers reaching far beyond the luminous disk. But the virtual Milky Way isn't a perfect mirror. There's a glaring mismatch, the missing satellites problem. Simulations predict thousands of dwarf galaxies orbiting the Milky Way, yet we've spotted only dozens. Where are the rest? Some may be too faint to see, cloaked in dark matter. Others might have been torn apart long ago, their stars scattered into the halo's streams. It's a reminder that even our most advanced models are works in progress, refining with every new discovery. Perhaps the most humbling insight is how fragile our galactic home truly is. Alter the dark matter's properties slightly, and the Milky Way might never have formed. Too much, and stars would cluster differently. Too little, and spiral arms would never take shape. These simulations don't just recreate the past, they hint at countless alternate universes where dark matter wrote a different story. Yet for all their power, these digital laboratories can't answer everything. They rely on assumptions about dark matter's nature. What if it's not what we think? The simulations evolve as theories do, each iteration peeling back another layer of the halo's mystery. So next time you gaze at the Milky Way, remember, the stars are just the prologue. The real story is still being written in the silent code of dark matter and the hum of supercomputers piecing it all together. Now let's turn our attention to a cosmic tug of war that's been quietly unfolding for decades. While dark matter has become the leading explanation for the galactic halo's gravity, not everyone is convinced it's the only answer. Enter modified gravity, a daring idea that suggests we might not need invisible matter at all. Perhaps our understanding of gravity itself is incomplete. At the heart of this debate is a theory called modified Newtonian dynamics, or MOND, proposed in the early 1980s by physicist Mordechai Milgram. MOND offers a bold alternative. Instead of invoking dark matter, it tweaks the laws of gravity at extremely low accelerations, like those found in the outskirts of galaxies. Picture this: when stars orbit far from their galaxy's center, Newton's familiar laws might subtly change, producing the extra pull we attribute to dark matter. It's as if the universe has a hidden rulebook for weak gravity, one we're just beginning to decipher. MOND appeal lies in its elegance. It successfully predicts the rotation speeds of many galaxies without requiring vast amounts of unseen matter. Take the Milky Way's outer stars. Their velocities align neatly with MOND predictions. No dark matter needed. Even more striking are ultra-diffuse galaxies, faint cosmic ghosts, where stars move inexplicably fast. MOND explains these naturally, while dark matter models struggle to account for their behavior. But the theory isn't without its challenges. When we zoom out to galaxy clusters, enormous gatherings of hundreds of galaxies, MOND falls short. These clusters exhibit gravitational effects so strong that even modified gravity can't fully explain them without adding some form of invisible mass. Then there's the cosmic microwave background, the afterglow of the Big Bang. Its intricate patterns align beautifully with dark matter's predictions, but leave MOND scrambling for adjustments. Dark matter, on the other hand, has become the Swiss Army knife of cosmology. It explains not just galaxy rotations, but also how galaxies clump together in the universe's large-scale structure. Computer simulations using dark matter recreate the cosmic web we observe, complete with voids and filaments. Yet dark matter has its own ghosts to reckon with. Despite decades of searching, no direct detection experiment has conclusively found a dark matter particle. We've built mile-deep labs, launched space telescopes, and still, the halo's true nature slips through our fingers like cosmic mist. This debate isn't just academic, it's a clash of scientific philosophies. Dark matter proponents argue we're missing a fundamental piece of the particle physics puzzle. Modified gravity advocates counter that we might be overcomplicating the cosmos, inventing invisible matter when a simpler tweak to gravity could suffice. Both sides agree on one thing: our current models are incomplete. Intriguingly, there might be middle ground. Some theorists explore emergent gravity, where gravity arises from the universe's underlying information structure, naturally mimicking dark matter's effects. Others ponder whether dark matter interacts in unexpected ways, or if multiple phenomena are at play. The galactic halo's mystery refuses to be pinned down, reminding us that the universe often defies neat categorization. What's remarkable is how this debate propels science forward. Each challenge to dark matter forces sharper tests and better models. Every MOND refinement pushes astronomers to observe galaxies in new ways. The tension between these ideas isn't a weakness, it's the engine of discovery, stretching our understanding of the cosmos. So where does this leave our galactic halo? For now, dark matter remains the leading explanation, but the door is wide open. Perhaps future telescopes will spot a dark matter particle's faint whisper, or maybe we'll uncover gravity's hidden chapters. Until then, the halo's true story dangles between two cosmic possibilities, each as tantalizing as the stars overhead. But let's peel back another layer of this cosmic mystery. If the galactic halo is indeed made of dark matter, what exactly is it? Scientists have proposed a menagerie of theoretical particles, each stranger than the last, that could form this invisible scaffold around the Milky Way. Leading the pack are weakly interacting massive particles, or WIMP. These hypothetical heavyweights are thought to be relics from the Big Bang, lurking in the halo's depths. Imagine particles 10 to 100 times heavier than a proton, yet so shy they barely interact with ordinary matter. A WIMP could pass right through you, or even Earth itself, without leaving a trace. Their ghostly nature explains why we haven't spotted them yet. They are cosmic introverts, avoiding attention at all costs. But their heft could give them just enough gravitational pull to sculpt galaxies. Then there's the Action, a featherlight contender with quantum quirks. Born from a theory solving a different puzzle in particle physics, actions would be billions of times lighter than electrons. Picture them as a cosmic fog, each particle vanishingly small, but trillions could be streaming through your hand this very second. Unlike WIMP, actions might reveal themselves through rare interactions with strong magnetic fields, morphing into fleeting bursts of light. Experiments like ADMS are essentially tuning a giant radio, hoping to catch the halo's faint whisper in this unfamiliar frequency. Some theories venture even further into the unknown. Sterile neutrinos, cousins of the nearly massless neutrinos we've detected, could be hiding in plain sight, their extra mass warping space subtly. Or consider SIMP, strongly interacting massive particles, which might clump together in ways that explain why some dwarf galaxies appear overloaded with dark matter. There's even wilder speculation. Primordial black holes, forged in the universe's first chaotic moments, could be peppering the halo like invisible boulders. What's astonishing is how these particles, if they exist, defy everyday experience. The halo isn't some distant abstraction. It's here now. Every square inch of Earth, including your body, might be experiencing a gentle rain of dark matter particles. They'd zip through your bones, your coffee cup, your bedroom walls without a single collision. You'd never feel them, yet collectively, their gravity holds the Milky Way together. This raises a tantalizing question. Could we ever catch one? Detectors buried deep underground, shielded from cosmic noise, wait patiently for the once-in-a-lifetime strike of a WIMP. Others hunt for actions by bathing powerful magnets in radio waves, hoping for an anomalous blip. So far, silence dominates, but that silence is telling. Each empty search narrows the possibilities, forcing us to refine our ideas about the halo's true composition. Perhaps the most humbling thought is this: dark matter might not be one thing at all. The halo could be a mix of particles, each contributing to the gravity we observe, or it might be something entirely unforeseen, a cosmic blind spot we've yet to imagine. Every night, as you gaze at the stars, remember, you're not just looking at the Milky Way's glittering disk. You're peering into the heart of an enigma, a halo of ghosts whose secrets are written in the language of gravity alone. Now let's descend into the depths where science meets the shadows. Far beneath the Earth's surface, shielded from the cacophony of cosmic rays and everyday radiation, lie some of the quietest places humanity has ever created. These are the underground labs hunting for dark matter, sanctuaries of silence, where even the faintest whisper of a particle could rewrite physics. Take the LUX experiment, nestled nearly 1 mile underground in a former gold mine in South Dakota. Here, a tank of ultra-pure liquid xenon sits in total darkness, waiting for the unimaginably rare moment a WIMP might bump into an atom. The setup is exquisitely sensitive, surrounded by layers of shielding to block stray particles. If dark matter is out there, LUX was designed to catch its minuscule fingerprint, a flash of light or a ripple of charge. Yet after years of listening, the detector heard nothing but silence. That absence, though, was a clue. It told scientists what dark matter isn't, narrowing the hunt. Then there's xenon, its successor, buried under a mountain in Italy. Picture a vat of liquid xenon, so pristine it's like a cosmic microscope. When a particle interacts with the xenon, it creates tiny bursts of light and electrons. Super-sensitive cameras and wires capture these signals, filtering out false alarms from natural radioactivity. The team has teased out hints, a handful of events that could be dark matter, but could also be mundane noise. That's the agony and allure of this search. The line between discovery and disappointment is razor thin. These experiments aren't just passive traps. They are feats of engineering, pushing the limits of detection. Some labs use crystals cooled to near absolute zero, where a single particle collision might raise the temperature by a sliver. Others, like Japan's Supercomputer, and monitor vast tanks of water for the faintest glow of Cherenkov radiation. What unites them is patience. Dark matter, if it interacts at all, does so grudgingly. Scientists might wait decades for one unambiguous signal, a single ping in the void. The thrill lies in the stakes. Catching a WIMP or action wouldn't just confirm the halo's makeup, it'd open a portal to physics beyond the standard model. Every null result, though frustrating, sharpens the search. It's like tuning a radio dial through static, knowing the song you're seeking might not even be on a known frequency. And so the detectors grow larger, purer, deeper. The next generation, like Darwin or LZ, will scan with even finer precision, probing the halo's secrets particle by particle. What's remarkable is how these labs embrace the unknown. They're built to find what we can't see, guided by math and hope. As you sit here now, particles from the galactic halo may be drifting through these detectors, and through you. The difference is, underground in the stillness, someone's watching, waiting, ready to catch the shadow that binds the stars. Let's rewind the cosmos to its earliest moments, where the seeds of the galactic halo were first sown. Picture the universe not as a vast, star-studded expanse, but as a hot, dense soup of particles just moments after the Big Bang. As this primordial fireball expanded and cooled, it left behind an echo of faint glow we now call the cosmic microwave background, or CMB. This afterglow is more than just a relic of the past. It's a treasure map, etched with clues about dark matter's invisible hand. The CMB is astonishingly uniform, but if you look closely, you'll spot tiny variations, ripples of slightly hotter and colder spots, like the surface of a pond disturbed by a gentle breeze. These fluctuations are cosmic fingerprints, revealing how matter was distributed when the universe was just 380,000 years old. And here's where dark matter enters the story. The gravity of these unseen particles sculpted those ripples, pulling ordinary matter into the patterns that would one day become galaxies and clusters. Without dark matter's extra gravitational oomph, those delicate wrinkles wouldn't have grown into the vast cosmic web we see today. Satellites like Planck and WMAP have mapped the CMB with breathtaking precision, turning those temperature variations into a blueprint of the early universe. The data shows that dark matter must have been 5 times more abundant than ordinary matter, just enough to explain why galaxies spin too fast, why clusters hold together, and why the universe looks the way it does. It's as if we're seeing the shadow of the galactic halo, cast 13.8 billion years ago, long before the Milky Way even existed. But the CMB doesn't just confirm dark matter's existence, it also tells us how it behaves. Those ripples reveal that dark matter must be cold, slow-moving compared to the speed of light. If it were hot, like fast-moving neutrinos, it would have smeared out the universe's structure, preventing galaxies from forming so early. Instead, the CMB's patterns match a universe where dark matter clumps together, creating gravitational wells for ordinary matter to settle into. This is why the Milky Way's halo isn't a smooth cloud, but a dynamic, lumpy scaffold, woven through with streams and substructures left over from its assembly. The cosmic microwave background also holds hints of dark matter's deeper mysteries. Some of its fluctuations don't quite fit our models, suggesting dark matter might interact with itself or with other forces in ways we haven't yet imagined. Could it decay into lighter particles? Could it carry a faint charge? These questions drive experiments like the Simons Observatory and future CMBS-4 project, which aim to measure the CMB's polarization, a subtler signal that might reveal dark matter's hidden quirks. What's extraordinary is how these ancient photons, traveling since the dawn of time, connect directly to the halo enveloping our galaxy today. The same dark matter that shaped the CMB's ripples also holds the Milky Way together, its gravity cradling stars and bending spacetime. Every time we look at the cosmic microwave background, we're glimpsing the origin story of the galactic halo, a tale written in the faintest whispers of the early universe, waiting to be decoded. Now, let's turn our gaze toward a tantalizing cosmic puzzle, one that blurs the line between shadow and light. Deep in the heart of our galaxy, something unusual flickers. Not the familiar glow of stars or the searing radiation of black holes, but an enigmatic excess of gamma rays, the universe's most energetic light. Could this be the halo's ghostly whisper, a sign of dark matter particles annihilating one another in the void? Or is it something more mundane, like a chorus of spinning neutron stars we've yet to fully understand? The answer is far from clear, but the mystery itself is a doorway to wonder. For over a decade, telescopes like NAS, a Fermi Gamma Ray Space Telescope, have detected a strange surplus of gamma rays emanating from the Milky Way's center. The signal is diffuse, spread across the galactic core like a faint, shimmering haze. At first glance, it matches what scientists might expect if dark matter particles were colliding and destroying each other, converting their mass into bursts of energy. After all, if dark matter is made of WIMP, weakly interacting massive particles, their rare interactions could produce gamma rays as a byproduct. It's a compelling idea, one that would finally give us a direct glimpse into the halo's hidden nature. But the cosmos is rarely so straightforward. Alternative explanations abound. Pulsars, the lighthouses of the galaxy, emit gamma rays as they rotate, and the crowded center of the Milky Way could harbor thousands of these unseen objects. There's also the chaotic region around Sagittarius, a star the supermassive black hole at our galaxy's heart, where intense magnetic fields and particle collisions might generate similar signals. The gamma-ray excess could even be the work of cosmic rays slamming into interstellar gas, a process that lights up the sky in ways we're still deciphering. The debate hinges on subtle details. If the signal were truly from dark matter, it should be smoothly distributed, tracing the expected shape of the halo's density. Yet some studies suggest the gamma rays cluster in ways that resemble discrete sources, like pulsars, rather than a uniform fog. Other researchers argue that the signal's energy spectrum, the specific colors of gamma rays present, aligns eerily well with predictions for certain dark matter particles. It's a cosmic Rorschach test. Depending on how you look at it, the data seems to support both conclusions. What makes this puzzle so thrilling is its stakes. If the gamma rays are indeed dark matter's farewell note, it would be one of the greatest discoveries in modern astrophysics, revealing not just what the halo is made of, but how it behaves. Yet even if the signal fades into the background of ordinary astrophysics, the search itself has pushed our understanding of the galactic center to new heights. Every contested paper, every refined telescope observation peels back another layer of the Milky Way's secrets, and so the question lingers, hanging in the darkness like the halo itself. Perhaps future observatories, like the Cherenkov telescope array, will spot telltale flashes in gamma rays or even neutrinos that finally crack the case. Or perhaps the glow will remain stubbornly ambiguous, a reminder that the universe guards its mysteries fiercely. Either way, the galactic center's eerie light invites us to keep looking, to keep questioning, because in the end, the pursuit of the unknown is just as vital as the answers we find. Now, let's step back and consider the bigger picture. What does this invisible halo truly mean for the Milky Way? Imagine our galaxy as a grand cosmic carousel, with stars whirling around its center at breathtaking speeds. But here's the mystery. Without an unseen hand holding everything together, this carousel should fly apart. The stars move too fast for the gravity of visible matter alone to keep them in orbit. That's where dark matter steps in, or rather, where it silently holds the reins. Think of the galactic halo as an enormous, invisible scaffold, its gravity weaving an unseen net that cradles the Milky Way. Without it, the delicate balance shatters. Stars at the edges of the galaxy, already racing at hundreds of kilometers per second, would simply drift into the void, untethered. The spiral arms, those glittering lanes of starlight we so admire, would unravel like a skein of yarn tossed into the wind. Over time, the Milky Way as we know it would dissolve, its stars scattering into the darkness like embers from a dying fire. But the chaos wouldn't stop there. Dark matter's gravity doesn't just bind stars, it shapes the very skeleton of the universe. Galaxies themselves are stitched into the cosmic web by filaments of dark matter, and without it, the entire tapestry would come undone. Neighboring galaxies, like Andromeda, which is on a collision course with us, would no longer feel the pull that draws us together. The great dance of galaxies, choreographed over billions of years, would fall into disarray. What's even more astonishing is how dark matter's influence stretches across time. When the Milky Way was young, It was the halo's gravity that gathered the gas and dust needed to forge the first stars. Without it, our galaxy might never have formed at all, and today, it continues to act as a cosmic anchor, stabilizing the Milky Way against the turbulent tides of passing galaxies and the shoves of invisible dark matter clumps lurking in the void. So what if dark matter vanished tomorrow? The changes would be catastrophic, but they wouldn't happen instantly. Light takes time to travel, and so would the news of dark matter's disappearance. We'd notice the effects first in the outer reaches of the galaxy, where stars would begin to stray from their orbits. Over thousands of years, the disruption would creep inward, like a slow-motion avalanche. The sun, tucked safely in one of the spiral arms, might not feel the effects for millions of years, but eventually, even our solar system would be cast adrift. Yet here's the comforting thought: dark matter isn't going anywhere. It's as much a part of the universe as space and time itself. Its presence, though invisible, is the reason we have a galaxy to call home. And while we may not yet know what it's made of, we can be certain of one thing: the Milky Way's dark halo is the unsung hero of our cosmic story, the silent force that keeps the stars alight and the galaxies whole. As we ponder this invisible architecture, it's worth remembering that the universe is full of such hidden dramas. The next chapter of our exploration takes us even further into the future, to a time when the Milky Way won't be alone, when another galaxy's dark halo will reach out and intertwine with our own. Now, let's peer far into the future, beyond the lifetimes of stars and even civilizations, to witness a cosmic event of unimaginable scale. 4 billion years from now, the Milky Way and Andromeda galaxies will begin their slow, inevitable dance toward one another, a collision written in the fabric of space itself. But this won't be a simple crash of stars and gas. Long before their luminous spirals touch, their dark matter halos will reach out like ghostly hands, intertwining in a gravitational embrace that reshapes both galaxies. Picture this: Andromeda, our nearest galactic neighbor, is hurtling toward us at nearly 110 kilometers per second. Yet despite this staggering speed, the vastness of space means the encounter will unfold over eons. As the galaxies draw closer, their dark matter halos each stretching hundreds of thousands of light years beyond their visible edges, will begin to overlap. Unlike stars, which rarely collide due to the immense distances between them, dark matter particles pass through one another effortlessly, their halos merging like mist, dissolving into mist. This silent merger will warp the very structure of both galaxies. The halo's gravity will tug at stars and gas, distorting the Milky Way's elegant spiral arms into chaotic streams. Over time, the two galaxies will stretch and twist each other like taffy, their shapes blurring as they orbit a shared center of gravity. Yet through it all, the stars themselves will remain untouched, drifting past one another unscathed. Space is so empty that even in a head-on collision, the chances of stars colliding are vanishingly small. What's truly fascinating is how dark matter dictates the timeline of this cosmic reunion. Simulations show that the halos will merge completely long before the visible galaxies do, their combined gravity setting the stage for the eventual stellar merger. Like invisible puppeteers, the dark matter halos will pull the strings, guiding the galaxies into a series of ever-tightening loops until, after billions of years, they settle into a single, elliptical galaxy, a quiet heavyweight of the local universe. This future galaxy, often nicknamed Milkdromeda, will bear little resemblance to the spirals we know today. The fierce gravitational tides will have erased their delicate structures, leaving behind a smooth, glowing orb of stars. Yet the dark matter halos, now fully merged, will remain as enigmatic as ever, still unseen, still holding the new galaxy together. Amid this chaos, there's a strange comfort. Our sun, if it still burns, will likely be flung into a new orbit, far from its current place in the Milky Way suburbs. Earth, if it survives, will witness a sky transformed, Andromeda's once distant smudge of light, swelling into a brilliant tapestry as the galaxies entwine. And though the collision sounds violent, it's really a slow, stately waltz, choreographed by dark matter's invisible hand. So while today we gaze at Andromeda as a faint smudge in the night sky, it's worth remembering it's not just a neighbor. It's a future partner in a dance that's already begun, its dark matter halo quietly stretching toward ours across the gulf of space and time. And when they finally meet, the universe will bear witness to a spectacle of gravity and light, a testament to the hidden forces that shape all things. But let's turn our gaze back to the present, where the Milky Way's dark matter halo is already shaping peculiar cosmic dramas. Hidden within its invisible embrace are rogue stars racing at unimaginable speeds, and ghostly galaxies so faint they barely whisper their presence. These aren't mere curiosities, they're clues to the halo's secret power. Take hypervelocity stars, for instance. These are stellar outlaws flung from the galaxy at speeds topping 2 million kilometers per hour, fast enough to escape the Milky Way's gravity entirely. How do they reach such velocities? The answer lies in the halo's unseen hand. Most of these stars were once part of binary pairs, orbiting the supermassive black hole at our galaxy's heart. When one star gets captured by the black hole, the other is catapulted outward like a slingshot, accelerated by the halo's immense gravitational field. Imagine a cosmic game of billiards, where dark matter is the invisible player, nudging stars into the void. Then there are the ghost galaxies, places like Dragonfly 44, a cosmic paradox discovered in 2016. This dim, sprawling galaxy weighs as much as the Milky Way, but emits only 1% of its light. The reason? 99.9% of its mass is dark matter. It's not alone. Dozens of these shadowy realms have been found drifting through the halo, their stars so sparse you could fly through one and barely notice. Without dark matter's gravity, they'd have disintegrated long ago. Their existence hints at a startling truth. For every luminous galaxy we see, there may be countless dark ones hiding in plain sight. Why does the halo let these oddities exist? The answer lies in its messy, dynamic nature. Dark matter doesn't distribute itself evenly. It clumps and folds, creating gravitational pockets that can fling stars to oblivion or cradle fragile galaxies. Some theorists even suggest hypervelocity stars might map the halo's structure, their trajectories tracing invisible tendrils of dark matter like breadcrumbs. And the strangeness doesn't end there. In 2018, astronomers spotted a star hurtling toward us at breakneck speed. Dubbed the Immigrant, It originated in another galaxy, likely torn loose during a long-ago encounter with the Milky Way's halo. Now it's a celestial hitchhiker, proof that dark matter's influence stretches beyond our galactic borders. These phenomena reveal the halo as more than a static backdrop. It's an active sculptor, bending the fates of stars and galaxies with its silent gravity. Somewhere in its depths, more rogue stars are being ejected, more ghost galaxies fading into the dark. And with every discovery, we glimpse the hidden rules of this shadowy realm, where the universe's most enigmatic forces are quietly at work. Now let's pull back the cosmic curtain and see the Milky Way's halo in its grandest context. It turns out this sphere of dark matter isn't isolated. It's part of something far larger, a hidden architecture that binds the universe together. Imagine the most intricate spider web you've ever seen, stretching across billions of light years, with galaxies clinging to its silken strands like dewdrops. This is dark matter's true masterpiece, the cosmic web. Scientists discovered this breathtaking structure not by seeing it directly, but by mapping the positions of millions of galaxies. When they plotted them in 3 dimensions, an astonishing pattern emerged. Galaxies weren't scattered randomly through space. They lined up along delicate filaments that intersected at dense nodes, forming a web-like structure spanning the observable universe. And here's the revelation. These filaments are made mostly of dark matter, with ordinary matter simply following their gravitational lead. The Milky Way's halo connects to this web through tendrils of dark matter that reach out like celestial highways. Our galaxy sits in a relatively sparse region, a cosmic suburb, with the closest major filament being the Pisces-Cetus supercluster complex, a ribbon of dark matter stretching over 1 billion light years. Along these filaments, galaxies march like pearls on a string, drawn together by invisible threads. Even the emptiest voids between filaments aren't truly empty. They contain ultra-diffuse dark matter, the web's faintest strands. What's truly mind-bending is how this web shapes cosmic evolution. When 2 dark matter filaments cross, their combined gravity creates a dense node where hundreds of galaxies can cluster. The Virgo cluster, our nearest massive galaxy group, sits at such a junction. Over time, these nodes grow as filaments funnel more matter toward them. Remarkably, computer simulations show this process beginning when the universe was just a baby-tiny quantum, fluctuations in the early cosmos, that dark matter amplified into the web we see today. The web also solves an ancient astronomical puzzle: why galaxies aren't evenly distributed. Before the web's discovery, scientists struggled to explain why some regions of space teem with galaxies while others are nearly deserted. Now we understand galaxies form where dark matter filaments intersect, leaving the voids between them relatively empty. Even now, the Milky Way is being gently pulled along a filament toward the Great Attractor, a mysterious concentration of mass about 250 million light-years away. Here's a thought to wrap your mind around. You're inside the web right now. Dark matter filaments pass through your body as you hear these words, unchanged and unnoticed. The Milky Way moves through this network at over 2 million kilometers per hour, riding currents we can't see. And somewhere out there, another civilization might be looking at their night sky, tracing the same cosmic threads that connect us all. The halo around our galaxy isn't just a feature, it's one knot in the universe's grandest tapestry. Now let's explore one of the most fascinating consequences of the Milky Way's dark matter halo, a phenomenon so powerful it bends the fabric of space itself. Picture this, a ray of light, traveling for billions of years from a distant galaxy, suddenly veers off course as it nears our galaxy. It's not magic, it's gravitational lensing, nature's own telescope, and the dark matter halo is its invisible lens. Einstein predicted this over a century ago. His theory of general relativity revealed that massive objects don't just pull on matter, they warp spacetime, altering the path of anything passing nearby, including light. The Milky Way's halo, with its immense but invisible mass, acts like a colossal lens. When light from faraway galaxies skims its edges, it doesn't travel in a straight line. Instead, it curves around the halo, creating surreal effects astronomers can detect. Here's how it works in practice. Imagine a distant quasar, a brilliant beacon from the early universe. As its light journeys toward us, some of it passes through the outskirts of our galaxy's dark matter halo. The halo's gravity bends that light, much like a glass lens bends sunlight. From Earth, we might see the quasar's image stretched into a faint arc, or even multiplied. In rare cases, the same galaxy can appear in multiple places at once, a celestial mirage. These distorted images are clues, letting scientists map the halo's mass distribution by measuring how severely it warps the light. One of the most striking examples is called an Einstein ring. When a distant galaxy aligns perfectly behind the halo's dense regions, its light gets bent into a complete circle, a golden ring in the sky. These rings are more than just beautiful. By studying their size and brightness, astronomers can weigh the dark matter, causing the distortion. It's like detecting a hidden object by the ripples it makes in a pond. But gravitational lensing isn't just about pretty patterns. It's a tool for uncovering the halo's secrets. For instance, some lenses reveal tiny clumps of dark matter within the halo, pockets of extra density that shouldn't exist if dark matter were perfectly smooth. These clumps mystify researchers. Are they remnants of smaller galaxies swallowed by the Milky Way long ago? Or do they hint at unknown properties of dark matter itself? The halo's lensing effects even help us peer further into the cosmos than normal telescopes allow. Like a magnifying glass, the halo's gravity amplifies the light of extremely distant objects, making faint galaxies visible that would otherwise be lost in the dark. In one famous case, a galaxy cluster's dark matter acted as a lens to reveal a star from the universe's first billion years, nicknamed Icarus, the farthest individual star ever seen. Yet not all lensing is dramatic. Much of it is subtle, a slight stretching of galaxy shapes across wide patches of sky. By studying these distortions in thousands of galaxies, scientists have created rough maps of the Milky Way's halo, showing where its gravity is strongest. These maps reveal something unexpected. The halo isn't a perfect sphere. It's lumpy, asymmetrical, as if shaped by ancient collisions we're only beginning to decipher. So next time you gaze at the night sky, remember, the stars aren't the only things out there bending light. An invisible hand, woven from dark matter, is reshaping the cosmos before your eyes, one distant galaxy at a time. Now let's turn our attention to a puzzle that has left astronomers scratching their heads for decades. According to sophisticated computer simulations, the Milky Way's dark matter halo should be teeming with thousands of tiny dwarf galaxies, each a faint, flickering satellite orbiting our galactic home. Yet when we peer into the night sky, we've only spotted a few dozen of them. Where are all these missing galaxies? Could they be hiding in plain sight, cloaked by dark matter? Or is there something fundamentally wrong with our understanding of the cosmos? This mystery is known as the missing satellites problem, and it started with the very simulations that helped us map the dark matter halo. When scientists recreated the Milky Way's formation on supercomputers, they expected to see vast numbers of small galaxies swirling around us, remnants of the universe's earliest structures. Dark matter's gravity would have pulled these tiny galaxies into orbit, much like planets circling a star, but reality didn't match the prediction. Instead of thousands, we found fewer than 60 dwarf galaxies so far. So why the discrepancy? One leading theory suggests these missing satellites aren't actually missing. They're just too dim for our telescopes to detect. Dark matter doesn't emit or absorb light, so if a dwarf galaxy is made mostly of this elusive substance, with only a handful of stars, it might be nearly invisible. Think of it like a city at night. If the streetlights are sparse, whole neighborhoods vanish into the dark. Some of these galaxies could be so faint that their starlight is drowned out by the Milky Way's glow. Another possibility is that many of these dwarf galaxies were torn apart long ago. The Milky Way's gravity is relentless, and over billions of years, it could have shredded smaller galaxies into streams of stars and dark matter, ghostly ribbons winding through the halo. We've actually spotted a few of these stellar streams, like the Sagittarius dwarf, which is slowly being absorbed by our galaxy. Could the rest of the missing satellites have met the same fate? Then there's the intriguing idea that dark matter behaves differently than we think. Most simulations assume dark matter is cold, slow-moving, and clumpy, which should have formed lots of small galaxies. But if dark matter is warm or faster-moving, it might have smoothed out the early universe, preventing so many dwarf galaxies from forming in the first place. This would mean our simulations are overestimating their numbers. The most tantalizing clue comes from galaxies like Dragonfly 44, a so-called dark galaxy discovered in 2016. It has about as much mass as the Milky Way, but emits barely any light, suggesting it's almost entirely dark matter. If more of these shadowy galaxies exist, they could account for the missing satellites, just not in the way we expected. Modern telescopes are now scanning the skies for these elusive objects, using methods like looking for subtle ripples in the Milky Way's outer gas clouds, or tracking the motion of distant stars. Each new discovery, or lack thereof, helps refine our understanding. Are the missing satellites simply too faint, already destroyed, or a sign that dark matter is stranger than we imagine? One thing's certain, solving this mystery won't just tell us where the dwarf galaxies went. It could reshape our entire picture of dark matter, galactic evolution, and the hidden architecture of the cosmos. So the next time you look up at the night sky, remember, there may be countless galaxies floating just beyond our sight, waiting to reveal their secrets. Now let's journey even further back in time, to an era when the universe was young and dark. Matter may have shaped the very first stars in a way we'd never expect. Picture this, not the blazing, fusion-powered giants we know today, but something far stranger, stars that burn with the ghostly light of dark matter itself. These theoretical objects are called dark stars, and if they existed, they would defy everything we thought we knew about how stars shine. Normally, stars light up because of nuclear fusion, hydrogen atoms smashing together in their cores, releasing energy as heat and light. But dark stars would operate on an entirely different principle. Instead of fusion, their energy would come from dark matter particles colliding and annihilating each other, producing a faint, steady glow that could last for millions or even billions of years. Imagine a star that doesn't burn out. While ordinary stars exhaust their fuel and die in spectacular supernovas, dark stars could have been incredibly long-lived, fueled by the vast reservoirs of dark matter in the early universe. They wouldn't blaze with the fierce intensity of modern stars, but would emit a cooler, more diffuse light, like embers in a cosmic fire. Some scientists suggest these stars could have grown to monstrous sizes, hundreds or even thousands of times larger than our sun, yet appearing dim and ghostly in the primordial darkness. Here's where it gets even more fascinating. Dark stars might have been the seeds for the supermassive black holes we find at the centers of galaxies today. If these stars eventually collapsed under their own weight, they could have formed black holes far more massive than any created by regular stellar collapse. That would explain how the universe had enormous black holes so early in its history, a puzzle that has troubled astronomers for years. But how would we ever find evidence of these phantom stars? After all, the first dark stars would have flickered out billions of years ago. The answer lies in the James Webb Space Telescope and its ability to peer back to the universe's infancy. If dark stars existed, their unique light signature, unlike anything produced by fusion, might still be detectable in the most distant, ancient corners of space. Some researchers are already scanning Webb's data for anomalies that could hint at these elusive objects. Of course, dark stars remain purely hypothetical for now, but their possibility opens a thrilling window into how dark matter might have shaped the universe in ways we're only beginning to grasp. If they are real, these stars would rewrite the story of cosmic dawn, showing that the first light in the universe didn't come from fusion at all, but from the silent annihilation of particles we still struggle to understand. So the next time you look up at the night sky, consider this. Long before the Milky Way's spiral arms took shape, before even the first ordinary stars ignited, the cosmos might have been illuminated by something far more mysterious. Dark stars, burning quietly in the void, their glow a whisper from the universe's deepest secrets. Now, let's turn our gaze closer to home and consider a haunting possibility. Could the Milky Way's dark matter halo be silently shaping the movements of our own solar system? As we drift through this vast, invisible ocean of particles, their collective gravity might be nudging planets, comets, and even our spacecraft in ways we've yet to fully grasp. Take a moment to picture the Oort cloud, that distant shell of icy debris surrounding our solar system. It's so far away that the sun's gravity barely holds sway, leaving these frozen remnants swaying like seaweed in a cosmic tide. Could the gentle pull of dark matter be influencing their orbits? Some scientists suggest that the halo's uneven distribution, clumpy and woven into filaments, might tug on these objects, subtly altering their paths over millennia. If true, this could explain why some comets deviate ever so slightly from their predicted trajectories, as if guided by an unseen hand. Then there's the puzzle of spacecraft anomalies. For decades, mission controllers have noticed something odd. Certain probes, like Pioneer 10 and 11, experience tiny but persistent deviations in their speed as they ventured into the outer solar system. Dubbed the Pioneer anomaly, this discrepancy was eventually attributed to heat radiation from the spacecraft's power systems, but not everyone is convinced. Could dark matter's gravitational influence be another piece of the puzzle? If the halo's density varies locally, it might create pockets of slightly stronger gravity, enough to tweak a spacecraft's course by fractions of a millimeter per second. It's a tantalizing thought, though one that remains speculative without concrete evidence. Even closer to home, dark matter might leave ghostly fingerprints on planetary orbits. While the sun's gravity dominates the inner solar system, the cumulative effect of trillions of dark matter particles passing through could, over billions of years, impart minuscule changes. Imagine the Earth's orbit as a spinning top, wobbling imperceptibly under these phantom tugs. The effect would be vanishingly small, far too faint to explain any known anomalies, but it's a reminder of how deeply the universe's hidden architecture might be woven into the fabric of our celestial neighborhood. Of course, the challenge lies in detection. Dark matter's gravitational influence is drowned out by the sheer mass of visible objects in the solar system. To tease out its signal, astronomers would need exquisitely precise measurements over vast timescales. Yet the quest is worth pursuing, for if dark matter does sculpt our solar system in subtle ways, it would offer a new window into understanding the halo's structure, and perhaps even the nature of the particles themselves. So as you ponder the night sky, remember this: the planets and comets dancing above you might not move solely under the command of the sun's gravity. Invisible threads, spun from the galaxy's dark matter halo, could be guiding them too, a whisper of the cosmos's deepest mysteries, echoing right here in our own celestial backyard. Now, let's tune our ears to the whispers of the cosmos, where dark matter's silent symphony plays on. Imagine the Milky Way's halo not just as a vast, invisible structure, but as a cosmic instrument, resonating with vibrations too deep for human ears to hear. These aren't sound waves in the traditional senses. Space is a near-perfect vacuum, after all but gravitational ripples, the echoes of colossal events that shaped our universe. Picture two black holes colliding billions of years ago, their violent merger sending shockwaves through spacetime itself. Like a stone dropped into a pond, these waves ripple outward, stretching and squeezing the fabric of the cosmos as they pass. When they reach the Milky Way's dark matter halo, something extraordinary happens. The halo, with its immense mass and sprawling structure, acts like a gigantic drumhead, vibrating in response to these ancient disturbances. These oscillations are incredibly subtle, stretching across thousands of light years and moving slower than a snail's pace. Yet, they carry secrets about the halo's shape, density, and even its history. Scientists call this phenomenon gravitational waves, and while we've detected them from black hole mergers, the halo's vibrations are far more elusive. They're not the sharp, chirping signals we've come to recognize, but a hum, a deep, persistent thrumming woven into the background of the universe. It's as if the halo is singing in a voice so low, we're only just learning to listen. To catch these whispers, researchers turn to some of the most sensitive instruments ever built. Projects like LIGO and the future LISA mission are designed to detect gravitational waves, but the halo's vibrations are a different beast. Their frequencies are so low, stretching over years or even centuries, that they're more like shifts in the cosmic weather than distinct notes. Some astronomers propose using pulsars, the ultra-precise cosmic lighthouses, as natural detectors. As gravitational waves pass through space, they subtly alter the timing of pulsars' flashes, creating a galaxy-wide network of ears tuned to the halo's song. What makes this symphony so fascinating is its potential to reveal the unseen. Just as a violin's vibrations can tell you about the wood it's made from, the halo's oscillations could unveil the nature of dark matter itself. Are the particles heavy or light? Do they bump into each other or glide past like ghosts? The answers might lie in the rhythm of these cosmic vibrations. So the next time you gaze at the night sky, remember, the silence of space is an illusion. Beneath the stillness, the Milky Way's dark matter halo vibrates with the echoes of cosmic collisions, a testament to the universe's hidden dynamism. It's a symphony without sound, a melody written in gravity, and we're only beginning to decode its notes. But let's turn our attention to another intriguing possibility. In the dark matter puzzle, particles so elusive, they're like whispers in a cosmic game of hide and seek. Among the many candidates for dark matter, actions stand out as one of the most fascinating. These hypothetical particles, born from theories trying to solve mysteries in particle physics, might just be the invisible architects of the galactic halo. Actions are ghostly things ultra-light, barely interacting with ordinary matter and drifting through space like a faint breeze. But here's the twist. Under the right conditions, they could reveal themselves by transforming into something we can actually detect: light. Picture a particle so shy, it only shows its face when placed in a strong magnetic field, where it might shimmer into existence as a photon. It's as if the universe handed us a cosmic decoder ring, turning the invisible into something we can see. To hunt for actions, scientists have built extraordinary machines that act like dark matter radios, tuning into frequencies we've never heard before. One of the most ambitious of these is the Action Dark Matter Experiment, or ADMX. Imagine a massive, supercooled cavity lined with powerful magnets, designed to resonate with the precise frequency an action might emit if it converted to light. Researchers slowly scan through these frequencies, listening for a faint signal amidst the cosmic noise. It's like tuning an old-fashioned radio dial, searching for a distant station. Only this station might broadcast the secrets of the universe. The challenge is immense. Action signals, if they exist, would be incredibly weak, drowned out by background interference from everything else in the cosmos. To combat this, ATMOS operates at temperatures colder than deep space, minimizing any stray vibrations that could mask the signal. It's a painstaking process, requiring patience and precision, but the payoff could be revolutionary. Finding actions wouldn't just solve the dark matter mystery, it would rewrite our understanding of particle physics itself. What makes actions so compelling is their dual nature. They were first proposed not to explain dark matter, but to fix a problem in quantum physics involving the symmetry of subatomic forces. It's a rare moment when a theoretical fix for one puzzle might also answer another, tying together the smallest scales of particle behavior with the largest structures in the cosmos. If actions are out there, they'd be the ultimate cosmic multitaskers, explaining both why galaxies hold together and why the universe's fundamental forces behave the way they do. Other experiments are joining the hunt, each with its own clever approach. Some use powerful lasers to probe for actions in the lab, while others look for their influence on starlight passing through magnetic fields in space. There's even a proposal to repurpose MRI machines, turning medical technology into action detectors. The creativity is as boundless as the mystery itself, with scientists leaving no stone unturned in their quest to catch these quantum shadows. So while the action remains hypothetical for now, the search is far from speculative. Every experiment, every tweak to the detectors, brings us closer to knowing whether these particles are the missing piece of the galactic halo. And if they are, it would mean that the dark matter enveloping our Milky Way isn't just an inert cloud, it's a sea of shimmering potential, waiting for the right conditions to reveal its hidden light. The hunt for actions reminds us that sometimes the universe's greatest secrets aren't hidden in the grand explosions or blazing stars, but in the quiet, almost imperceptible flickers at the edge of our perception. And with each experiment, we're learning to listen just a little better. Now, let's peel back another layer of the galactic halo's enigma, one that involves not just what's missing, but what's unexpectedly there. Deep in the void, scientists have stumbled upon a strange surplus of antimatter, specifically positrons, the antimatter twins of electrons. These particles shouldn't exist in such abundance, yet they're raining down on our detectors like cosmic breadcrumbs, hinting at something even more extraordinary. Dark matter might be decaying right before our eyes. Picture the universe as a grand crime scene. The clues are subtle tiny spikes in positron counts, picked up by instruments like the Alpha Magnetic Spectrometer aboard the International Space Station, or the payload for antimatter-matter exploration and light nuclear astrophysics, PAMELA, mounted on satellites. These detectors act as cosmic fingerprint scanners, catching antiparticles that shouldn't be there in such numbers. Ordinary astrophysics can't fully explain them. Supernova and pulsars might produce some, but the sheer volume of positrons suggests another culprit, one lurking in the dark matter halo itself. Here's where the plot thickens. Some theories propose that when certain types of dark matter particles collide, they annihilate each other, releasing a burst of energy that morphs into positrons and other particles. It's like catching the echo of a shadowy explosion, one we can't see directly, but whose aftermath drifts toward us. Other models suggest dark matter might slowly decay over eons, shedding positrons like a crumbling monument. Either way, these antimatter excesses are tantalizing hints that the halo isn't just a static cloak, it could be a dynamic, even self-destructing entity. But as with any good mystery, the evidence is maddeningly ambiguous. The positron signal could also come from undiscovered pulsars or other exotic astrophysical objects. To crack the case, scientists are cross-examining the data with painstaking precision. They're studying how the positron count changes with energy levels, searching for telltale patterns that might betray dark matter's involvement. A sudden drop-off at high energies, for instance, could point to a specific mass of dark matter particles, narrowing down the suspects. The stakes couldn't be higher. If dark matter is indeed behind this antimatter drizzle, it would mean the halo is subtly interacting with itself, a revelation that would upend our understanding of its nature. Most models assume dark matter is cold and inert, drifting past other particles like ships in the night. But if it's annihilating or decaying, it implies forces at work we've yet to fathom. This detective story isn't confined to space. Underground labs are joining the hunt, repurposing neutrino detectors to look for faint signals linked to dark matter decays. Even the Large Hadron Collider is in on the action, smashing protons together in hopes of producing dark matter particles, or their telltale byproducts, in miniature. Every experiment is another line of inquiry, another chance to corner the truth. So while the antimatter mystery remains unsolved, it's a reminder that the galactic halo isn't just a silent spectator. It might be whispering to us through these rogue positrons, leaving a trail we're only beginning to follow. And with each new piece of data, we're one step closer to answering the ultimate question. Is dark matter not just the unseen scaffolding of the cosmos, but an active player in its hidden dramas? The search continues, not with flashy explosions or blazing lights, but in the quiet accumulation of anomalies, each one a potential key to the halo's darkest secrets. Now, let's turn our gaze to another captivating possibility hidden within the galactic halo, one that takes us back to the very dawn of time. Imagine if dark matter isn't made of exotic particles at all, but instead consists of ancient relics from the universe's explosive birth, primordial black holes. These aren't the black holes formed from collapsing stars, but ones that might have emerged in the chaotic first moments after the Big Bang, woven into the fabric of space itself. Picture the early universe as a seething cauldron of energy, where density fluctuations could have collapsed into tiny, dense knots of matter. Some of these knots might have been so extreme that they birthed black holes, some as small as an atom, others as massive as a star. Unlike their stellar counterparts, these primordial black holes wouldn't glow with the heat of infalling gas or announce themselves with brilliant accretion disks. They'd be nearly invisible, drifting through the galactic halo like phantoms. The idea isn't as far-fetched as it sounds. In fact, it's a tantalizing solution to the dark matter puzzle. If enough of these primordial black holes exist, their collective gravity could explain the halo's invisible mass. They'd orbit the Milky Way just like stars or gas, tugging on visible matter without emitting a shred of light. But how do we hunt for something so elusive? Scientists have devised clever ways to spot them. One method relies on gravitational microlensing, a phenomenon where a black hole passes in front of a distant star, bending and briefly amplifying its light like a cosmic magnifying glass. Surveys like the optical gravitational lensing experiment have scanned millions of stars for these telltale flickers, but so far, the results are inconclusive. Too few black holes have been found to account for all the dark matter, though they could still play a partial role. Another clue comes from the cosmic microwave background, the afterglow of the Big Bang. If primordial black holes were abundant in the early universe, their evaporation or interactions might have left subtle imprints in this ancient light. So far, no such fingerprints have been detected, but the search continues with ever more sensitive instruments. And then there's the merger of black holes detected by gravitational wave observatories like LIGO. Some of these collisions could involve primordial black holes, though again, the evidence is still ambiguous. What makes this theory so compelling is its sheer simplicity. It doesn't require inventing new particles or forces, just extending our understanding of black holes to the universe's earliest moments. Yet it's also fraught with challenges. Primordial black holes would need to form in just the right numbers and masses to match observations, and their presence would have had to avoid disrupting other cosmic processes, like the formation of the first stars or the distribution of galaxies. Still, the possibility lingers like a ghost in the data. If even a fraction of the galactic halo's mass is tied up in these ancient black holes, it would mean we're surrounded by silent time capsules from the Big Bang itself, each one a frozen fragment of the universe's violent infancy. And as our tools grow sharper, from next-generation gravitational wave detectors to space telescopes, peering deeper into the cosmos, we might finally uncover their shadowy presence. So while the mystery endures, it's a reminder that dark matter could be hiding in plain sight, not as an undiscovered particle, but as something even more enigmatic. Black holes born from the first breath of time, waiting silently in the dark. Now, let's bring this cosmic mystery a little closer to home, right into our very bodies. If dark matter fills the galactic halo and permeates the universe, then it must also be streaming through you and me at this very moment. Picture trillions of these ghostly particles passing effortlessly through your skin, muscles, even your bones, like whispers in the wind. It's a strange thought, isn't it? That as you sit here, an invisible tide from the depths of space is flowing through you, unnoticed and unfelt. So, could these particles actually affect us? The short answer is probably not, but the long answer is far more fascinating. Most dark matter candidates, like WIMP or actions, interact so weakly with ordinary matter that they'd rarely leave a trace. A WIMP, for instance, might collide with an atom in your body once in your entire lifetime, if at all. Actions, if they exist, would be even more elusive, flickering through matter like faint shadows. Even if dark matter particles did interact slightly more often, their effects would be dwarfed by the constant bombardment of cosmic rays and neutrinos we already experience. But let's indulge the idea for a moment. If dark matter did interact just a tiny bit more strongly, could it influence biology? Some theorists have playfully speculated that rare interactions might cause subtle mutations in DNA over millennia, potentially shaping evolution in ways we can't yet detect. Others wonder if dark matter could accumulate in the Earth's core or even within living cells, though there's zero evidence for such phenomena. It's a reminder of how little we truly know. Dark matter's invisibility doesn't just hide it from telescopes. It hides its potential role in the microscopic workings of life itself. What's truly remarkable is how this idea bridges the cosmic and the personal. The same particles that hold galaxies together are, in a way, intimate strangers to us, always present, yet always just out of reach. And while they may not stir our biology, they stir our imagination. Imagine if we could sense them. Would the halo feel like a breeze, a hum, or just the quiet weight of the universe pressing in? Of course, science thrives on testable ideas, not just poetry. Experiments like Cosine 100 and Gamma/Libra have sought signs of dark matter interacting with Earth-bound materials, from crystals to liquid xenon. So far, their results are contradictory or inconclusive, leaving the question open. But every null result tightens the constraints, telling us what dark matter isn't, and inching us closer to what it might be. So the next time you look up at the night sky, remember, you're not just an observer of the cosmos. You're part of its grand, unseen flow, a temporary vessel for particles older than stars. Dark matter may not shape your body, but it certainly shapes the galaxy you call home, and in that way, it's already a part of your story. Now, as we ponder our place in this vast, invisible web, let's turn to another question that has captivated both scientists and storytellers alike. How has the mystery of unseen cosmic forces shaped human culture and myth? From ancient legends to modern sci-fi, the idea of hidden realms and phantom influences echoes our timeless fascination with the unknown. Long before science gave us the language of dark matter, humanity wove stories about the unseen threads binding the cosmos. Cast your mind back to ancient Norse myths, where Yggdrasil, the great world tree, stretched its roots and branches across the realms, a living scaffold holding everything together, invisible yet essential. Doesn't that sound familiar? Like the dark matter halo, Yggdrasil was the hidden architecture of the universe, felt but never seen. Across cultures, people envisioned forces beyond their sight. The Greeks spoke of the ether, a luminous fifth element permeating the heavens. Polynesian navigators trusted the Aveki, a spiritual current guiding their voyages, much like dark matter's gravity steers galaxies. Even in Hindu cosmology, the serpent Ananta floated in the void, cradling the world, a poetic echo of how the Milky Way rests in its dark matter embrace. These weren't just tales, they were humanity's first attempts to explain the inexplicable, to name the nameless. Fast forward to modern times, and science fiction has picked up the torch. Think of Star Trek's subspace, or the Force in Star Wars, invisible energies that connect everything. Philip Pullman's Dark Materials trilogy literally made dust the source of cosmic mystery. These stories resonate because they tap into the same awe we feel when scientists describe the halo, an unseen presence shaping reality. But here's the twist. Unlike myths, dark matter isn't magic. It's a puzzle we're chipping away at with math and telescopes. The ancients attributed eclipses to dragons. We predict them down to the second. Yet both share that primal curiosity. What else is out there, hidden in plain sight? Consider how art reflects this too. Van Gogh's Starry Night swirls with unseen currents, while composers like Holst captured the planet's motion. Music for celestial mechanics, we now know dark matter governs. Even horror isn't immune. Lovecraft's elder gods lurk in the voids between stars, much like the halo's particles lurk in the spaces between atoms. Perhaps that's why dark matter captivates us. It's not just physics, it's the latest chapter in an age-old story. Every culture has its version of the invisible hand that builds and binds, and now we've given it a name, even if we haven't quite met it yet. The halo isn't just around the Milky Way, it's woven into our collective imagination, a reminder that some mysteries transcend time. Now, as we stand on the brink of new discoveries with tools like the Vera Rubin Observatory, we're not just hunting particles. We're answering questions that began around campfires millennia ago. The next time you hear a legend about the unseen world, smile. You know the real story is even stranger. And with that, let's turn our gaze to the future, where cutting-edge telescopes promise to map the invisible like never before. The quest to unravel the galactic halo's secrets is about to leap forward with a new generation of eyes on the cosmos. Imagine stepping into a room where the lights slowly brighten, revealing shapes you never knew were there. That's what tools like the Vera Rubin Observatory and the Euclid spacecraft promise to do for dark matter. These aren't just upgrades, they're revolutionaries, designed to see the universe in ways we've only dreamed of. Take the Vera Rubin Observatory, perched high in Chile's dry mountains. Its centerpiece is the largest digital camera ever built, a 3,000 megapixel behemoth that will photograph the entire southern sky every few nights. But here's the magic. It won't just snap pretty pictures. By tracking how billions of galaxies subtly warp the light behind them, an effect called gravitational lensing, it'll trace the halo's invisible scaffolding with razor-sharp precision. Think of it like watching ripples on a pond to deduce the shape of the submerged rocks causing them. Over a decade, this single instrument could map dark matter's distribution across a quarter of the visible universe, exposing filaments and voids we've never glimpsed. Then there's Euclid, the European Space Agency's dark matter detective, set to orbit 1,000,000 miles from Earth. While Rubin scans wide, Euclid zooms deep, measuring the distortion of over 1 billion galaxies with infrared and optical lenses. Its specialty, capturing the faintest, most distant light bent by dark matter's gravity, light that's been traveling since the universe was half its current age. Together, these missions will cross-check each other's findings, like two detectives comparing notes to crack a case. But the innovation doesn't stop there. NASA's Nancy Grace Roman Space Telescope, launching later this decade, will combine Rubin's wide gaze with Euclid's sensitivity, hunting for primordial black holes that might lurk in the halo. And on the ground, Instruments like the Square Kilometer Array radio telescope will listen for dark matter's echo in the hydrogen gas between galaxies, a whisper of how the halo tugs on ordinary matter. What makes this era extraordinary isn't just the technology, it's the collaboration. For the first time, astronomers, physicists, and computer scientists are pooling data from multiple telescopes, feeding it into supercomputers to build universe-scale simulations. These digital twins let us test theories in seconds that would take nature billions of years. If dark matter behaves differently than we think, these models will spotlight the discrepancies, guiding us toward new answers. Yet the most thrilling possibility is the unexpected. Every time humanity has built a better window to the cosmos, from Galileo's telescope to Hubble, we've stumbled upon surprises. Maybe these new tools will catch dark matter particles interacting in ways we can finally detect. Or perhaps they'll reveal that the halo isn't just a smooth cloud, but riddled with intricate substructures like cosmic coral reefs. One thing's certain, the halo story is far from finished. As these instruments peer into the dark, they're not just collecting data, they're continuing humanity's oldest conversation with the unknown. And just as the ancients painted their visions of the unseen, we're sketching ours with mathematics and light, inching closer to the day when dark matter steps out of the shadows. Now, consider this. What if the biggest revelation isn't about dark matter itself, but how it reshapes our understanding of reality? The answers may be closer than we think, waiting in the starlight these telescopes are about to catch. Now, as we stand on the edge of discovery, let's pause and look at the unanswered questions still swirling around the galactic halo. For all the progress we've made, dark matter remains a puzzle with missing pieces, each mystery pulling us deeper into the unknown. Take the most pressing question: why, after decades of searching, haven't we detected dark matter directly? Underground labs like LUX and Xenon have waited in silence, their detectors chilled to near absolute zero, hoping to catch the faintest whisper of a dark matter particle colliding with ordinary atoms. Yet so far, nothing. Some scientists wonder if we're looking for the wrong thing. Maybe dark matter isn't a single type of particle, but a whole family, each slipping past our instruments like ghosts through a wall. Others suggest these particles might interact with us even more weakly than we imagined, requiring detectors more sensitive than anything we've built yet. Then there's the puzzle of dark matter's behavior. Does it interact with itself, or is it truly as aloof as it seems? Most models assume dark matter particles pass right through each other, but what if they occasionally collide, creating faint signals we've overlooked? Some astronomers point to oddities in galaxy clusters, where dark matter appears to lag behind visible matter during collisions, a hint that it might feel forces beyond gravity. If true, this would rewrite the rules we've assumed for decades. And what about the possibility that dark matter isn't one thing, but many? Imagine a cosmic zoo of particles, some heavy and slow, others nearly massless, streaming through the halo at different speeds. This could explain why no single experiment has found it. We might need a whole toolkit to uncover each piece. There's even speculation that some dark matter could be primordial black holes, left over from the universe's first moments, hiding in plain sight. The halo's structure adds another layer of intrigue. Simulations predict it should be clumpy, littered with countless small sub-halos orbiting like moons around the Milky Way. Yet when we look, we find far fewer than expected. Are these missing clumps too faint to see, or does dark matter behave differently on small scales, smoothing itself out in ways we don't yet understand? Perhaps the biggest question is whether dark matter is even the right answer. Could gravity itself work differently on galactic scales, as theories like modified Newtonian dynamics suggest? While most evidence still points to dark matter, the fact that we're still debating this after 80 years shows how deep the mystery runs. These aren't just academic riddles, they're clues to the universe's blueprint. Every unanswered question is a signpost on the frontier of knowledge, reminding us how much we still have to learn. With each new telescope, each sharper simulation, we're peeling back another layer of the halo's secrets. And one day, when the pieces finally click into place, we might find that the truth was stranger than anything we've dreamed. So let's embrace the questions, for they are what drive us forward. After all, the most thrilling part of any mystery isn't the answer, it's the hunt. Now, let's take a moment to drift, not just with our thoughts, but with our imagination. Picture yourself suspended in the vast, silent expanse of the Milky Way's halo, cradled by something invisible yet immense. Around you, the galaxies' glittering spiral arms stretch like a distant shore, but here, in the darkness between stars, you're floating through an ocean of secrets. Close your eyes and imagine the particles countless, ghostly, streaming past you like a cosmic wind. They don't glow, they don't collide, they simply are, weaving through space and even through you, as if you're no more solid than a shadow to them. These are the building blocks of the galactic halo, the unseen threads holding our galaxy together. If you reached out, your hand would pass through them, yet their collective gravity is the only reason stars haven't spun away into the void. The longer you linger here, the more you sense the halo's architecture. It's not uniform, not empty. Simulations tell us it's a tapestry of dense rivers and faint tendrils, remnants of smaller galaxies swallowed by the Milky Way long ago. Somewhere in this darkness, there might be clumps of dark matter so dense they bend starlight, or faint echoes of ancient collisions that sent ripples through the halo's fabric. And then there's the silence. No hum of energy, no crackle of radiation, just the quiet pull of gravity, imperceptible yet unshakable. This is the paradox of dark matter. It shapes everything, yet leaves no trace for our eyes or instruments to catch. It's the universe's most patient sculptor, working over billions of years, never rushing, never faltering, but the halo isn't static. It breathes in a way. As the Milky Way rotates, the dark matter swirls with it, a slow, cosmic dance. Some particles might be ancient, dating back to the universe's first seconds, while others could have been flung here from galaxies far beyond our own. If you listen closely, not with your ears, but with your imagination, you might hear the faintest vibration, a gravitational whisper from the halo's depths. What would it feel like to truly know this place, to see the invisible currents, to map the paths of particles we can't detect? For now, it remains a dream, a thought experiment wrapped in mystery. But that's the magic of the galactic halo. It invites us to wonder, to question, to let our minds wander where our technology can't yet follow. So as you float here, remember, you're not just imagining emptiness. You're envisioning the hidden foundation of our galaxy, the scaffolding of the cosmos itself, and perhaps in that quiet darkness, you'll find not just answers, but new questions, the kind that keep us reaching for the stars. Now, let's settle into the quiet embrace of the cosmos, where the Milky Way's dark halo has been Earth's unseen guardian since the dawn of time. Think of it as a lullaby sung in gravity, a constant, gentle pull that has cradled our solar system through countless revolutions around the galaxy's heart. While stars blaze and planets whirl, the halo remains, a silent sentinel in the depths of space, its presence as steady as the rhythm of tides. There's something profoundly comforting in this thought. Long before cities lit up the night or telescopes pierced the sky, dark matter was already here, weaving its invisible threads through the fabric of our galaxy. It watched as Earth formed from dust and fire, as oceans filled and life stirred. It witnessed the rise of mountains and the drift of continents, all while holding the Milky Way together with its ghostly grasp. The halo doesn't hurry, it doesn't falter, it simply is, a testament to the universe's quiet endurance. Close your eyes and imagine this constancy. Across billions of years, as galaxies collided and stars flared out, the halo persisted. Its particles older than sunlight, older than atoms, drifted through epochs unchanged. They were here when dinosaurs roamed, when the first humans gazed upward in wonder, and they'll still be here long after our stories are forgotten. There's a solace in that, a reminder that some things transcend time. The unknown isn't always frightening. Sometimes, it's what keeps the cosmos in balance. And just as the halo cradles the Milky Way, it cradles us. Every second, streams of dark matter pass through your body, harmless and unfelt, like whispers from the void. You can't see them, but their gravity tugs ever so slightly on the planets, on the sun, on the very path Earth takes through space. In a way, we're all dancing to the halo's silent tune, a slow, celestial waltz set to the universe's oldest music. So tonight, as you drift toward sleep, let the thought of the galactic halo wrap around you like a cosmic blanket. It's a reminder that you're part of something vast and mysterious, yet profoundly steady. The same forces that shaped galaxies also cradle your quiet moments, weaving the ordinary and the extraordinary into the same story. And perhaps in that stillness, you'll find not just wonder, but peace, knowing that even in the dark, the universe holds you close. As we come to the close of our cosmic journey tonight, let's take one last look at the invisible embrace of the Milky Way's dark halo. This vast, mysterious sphere of dark matter, unseen yet undeniably present, holds our galaxy together like an ancient, silent guardian. It's a humbling thought, isn't it, that for all our curiosity and exploration, so much of the universe still eludes our understanding. The galactic halo is a reminder that some of the cosmos' most profound truths linger just beyond our grasp, hidden in plain sight. Think of everything we've wandered through tonight, the way dark matter's gravity shapes galaxies, how it threads the universe in an intricate web, and how its particles drift through us unnoticed, like ghosts passing through walls. We've glimpsed the edges of a mystery that defies even our most advanced science, a puzzle wrapped in the quiet darkness of space. And yet, there's beauty in not having all the answers. The unknown isn't something to fear. It's an invitation to wonder, to keep looking up and asking questions. So as you let your thoughts settle tonight, imagine the halo's gentle pull, steady as a heartbeat, cradling the Milky Way in its unseen arms. Picture those streams of dark matter flowing around you, as timeless as the stars, connecting you to something far greater than yourself. Whether you're dreaming of colliding galaxies or simply drifting into quiet rest, remember this: the universe is vast, mysterious, and full of secrets waiting to be uncovered. And for now, that's enough. Close your eyes and let the stillness of the cosmos carry you. The same forces that bind galaxies together also whisper through your quietest moments, a reminder that even in the deepest dark, we're never truly alone. Sleep well, wrapped in the enigma of the galactic halo, and may your dreams be as boundless as the universe itself. If you've enjoyed this journey through the stars, don't forget to like, subscribe, and hit the notification bell so you never miss another celestial adventure. Until next time, good night and sweet dreams among the mysteries of the cosmos. you.